So, in today's lesson, we're going to be doing Euclidean geometry. And let's see the question that we have got. We have question 8. It says, in the diagram, point A, B, D, and C lie on a circle C, where CE is parallel to AB, with E on AD produced. Chord CB and AD intersect at F. D2 is equals to 50 degrees and C1 is 15 degrees. We can all see that, right? So here you can see that we've been given a pair of parallel lines. Then we have this, it's parallel to AB. Now, when we have parallel lines, we know maths is fun with parallel lines, right? So whenever we have parallel lines, this is what we think of, fun, whereby we'll check if we have any corresponding angles, any co-interior angles, or any alternate angles, right? But if you can check here, if you can just continue here, you will see that definitely you have alternate angles, which the whole of C1 and C2 will be equal to the whole of B, right? So those are your alternate angles. Your alternate angles are always equal. Do we have another Z forming? If you can just check like this, from this side here, we do have another Z forming. So that means the angle B as a whole will be equal to the angle E as a whole will be equal to angle A. So this angle E will be equal to angle A, again for alternate angles on the same pair of parallel lines, right? So 8.1 says calculate with reason the size of A, right? So from the green Z, we can see that in order to get to A, we must get to E first. So we must find a way of linking E to A, right? But if you can check here, this here is a what? Is a triangle, CED. Then if you can just extend it here, you will see that this triangle is an exterior angle here. Now we know from our knowledge of triangles that an exterior angle of a triangle must be equal to the two opposite interior angles. You can see that case here whereby our D2 will be equal to what? Will be equal to C1 plus E. The reason being what? Exterior angle of triangle, right? So this exterior angle must be equal to the two opposite interior angles of a triangle. Now that we have that, we can just go, okay, what's our D2? Our D2 is 50 degrees. But what's my C1? My C1 is 15 degrees. Then now I'm looking for E. In order to calculate my E, I'm just gonna go E is 50 minus 15 degrees. Then my E is obviously gonna be 35 degrees. But then the question is not looking for E, I'm looking for A. Now that I've concluded that I have parallel lines, and here I have what? A Z forming. That means whatever I get for A will be the same value for, whatever I get for E will be the same value for A, right? Why? Because these are alternate angles. Then I say A is equals to E. What's the reason? Alternate angles. For which parallel lines? CE parallel to AB, right? Therefore, what's my A? Therefore, my A is equal to 35 degrees, right? And that's how you could have solved that one. Then let's go to C2. C2 is just here, right? But then if you can check here, there is an angle D2 that we are given here, subtended by what? By CA, right? So subtended by this sec subtended by this segment or this arc CD, and then we have CD again subtending the arc CD subtending B, right? Now we can conclude that since D2 and B are subtended by what? The same arc CA, they must be equal. Then we can say D2 is equals to angle B. Why? Because they are angles on the same segment, right? Making our B what? 50 degrees. Then our B is 50 degrees, right? Now, if we have our B at 50 degrees, and then we said we have this pair of parallel lines forming a Z here, right? Meaning now the angle B must be equal to the whole of angle C, right? So we're gonna go, but angle B is equals to C1 plus C2. What reason? Alternate angles of, so these are alternate angles, and then what are the pair of parallel lines from which these alternate angles occur? So it's CE parallel to AB. Then what's my C1? My B, I have 50 degrees. C1 I'm given to be 15. I'm looking for C2. So C2 is 50 minus 15, which will be 35 degrees, like that. So my C3 is 35 degrees. Now what else? 8.2 says prove with a reason that CF is a tangent to the circle passing through points C, D, and E. So the first thing we need to do is construct a circle that will go through those points. Okay. That will go through those points. So we have a circle like that touching C, D, and E, right? Now they're saying CF is a what? Is a tangent. This CF that you see here is a tangent. Now, how are we going to prove that CF is a tangent? Of course, in this case, we can see there is an angle C2 forming between the tangent and a chord that is inside what? The circle, right? Now we know what theorem is associated with that is the theorem of the tan chord, which says if I have an angle forming within in between your chord and the tangent, then that angle must be equal to the angle on the alternate segment. How do we find the angle on the alternate segment? Just hold the ends of the chord, and then where they will join, where they will meet, that's where the alternate segment is. So the alternate segment here is angle E, right? So in other words, we must prove that C2 is equal to angle E. But then we have already proven that from the question above, right? C2 is equal to angle E, and then we found that they were both what? 35 degrees, right? Now, having that case, we can now conclude that CF is a tangent, right? CF is a tangent. From what basis are we saying that CF is a tangent? From the converse. From the converse of the tan chord theorem. From the converse of the tan chord theorem.